Welcome back to ME 760 Engineering Analysis 1. So last time we just discussed the similarity transformation, and the main idea behind similarity transformation is to be able to transform a matrix A, for example, in a set of bases E sub I or sub J, to another matrix B in another set of linear bases, let's say E prime J, and the new matrix that you will be transformed, B for example, will be much simpler to handle compared to the original matrix A, for example. So if we have the original matrix A, for example, is a sparse matrix and it has millions, let's say A11, A12, A13, and so on up to A1n, then A21, A22, A23, up to A2n, and so on until AN1, AN2, AN3, up to ANn. Let's assume that this matrix is a result of a matrix that we got from a linear set of equations that we want to solve. So those would be the coefficients for the n by n, let's say, n number of equations in n unknown. So in this case, if this is something like million equations, for example, in million unknown or whatever, it's a huge, very huge matrix. It will be extremely difficult to be able to solve such matrix. So the similarity transformation S minus 1 AS will help us transform this matrix A to a new matrix B. So using this, we will be able to transform matrix A to matrix B, where matrix B, for example, will be just, let's assume that it will be just the diagonal of the old matrix. So we transformed matrix A to matrix B using the similarity transformation. And matrix B, last time we stated that matrix B will have the same property as matrix A. Last time we showed that if the matrix A is the identity matrix, matrix B should be the identity matrix. If matrix A that has a determinant, so the matrix B will have the same determinant. And we show a couple of properties. Today we will finish the last property, which will be the trace. So the trace of matrix A should be exactly the same like trace of matrix B. Although matrix A and B are completely different matrices, but they are similar. And the beauty of the similarity transformation is you will be able to transform a sparse matrix, which has lots of elements inside the matrix, to a diagonal matrix. And if you have a diagonal matrix, hey, that's it. If this is x1, x2, up to xn, you transformed your equation, set of equation, to a very trivial solution here. Or what you will do is you say what? A11, x1 is equal to y constant c1. A22, x2 equal to c2. A33, x3 equal to c3. Very easy. You will get the solution right away. So this is the beauty of the similarity transformation. So for those of you who are, for example, confused or just were asking, oh, this is extremely abstract, why we use those similarity matrices? This is the usage of similarity matrices. And we will continue this during this lecture to show a couple of examples where we will have non-degenerate eigenvectors or eigenvalues, and the case where we will have a degenerate eigenvalues, how to solve and reduce a form like this to a form like this, and then solve for the set of equations. So let's just show. So the similarity transformation, as I just stated, we will be transforming a matrix like this to a matrix like this, and this matrix is called diagonal matrix. So let's show how to do matrix diagonalization. So matrix diagonalization. Before I go to the matrix diagonalization, let me just put the last property from last time. So the last property is if B and A are similar matrices, then the trace of B should be equal to the trace of A. What's the definition of trace when we defined it a couple of lectures ago? So the summation of the diagonal elements of the matrix. So here it is. The trace of B will be just the summation of the diagonal element of B, which is BII. And this will be summation from I over the summation of J over the summation of K. And what's B? The matrix B. The matrix B is formed from the similarity transformation of the matrix A. So this is Sij AJK SKI. So this is nothing more than B, and this is the similarity transformation because P equal to the similarity transformation. So in this case, this will be summation for I, summation for J, and summation for K, and then this will be the Sij multiplied by the Ski. So if you sum over this one, this one is nothing more than the components of the identity matrix I, J, K, and if you sum it over all AI, so this should give you the summation of J, summation of K, and this will give you the canonical delta function J, K of AK. So the I, J, K, the summation over I, this will give you the canonical delta function, and then when you decompose this, the canonical delta function multiplied by A, J, K, this will just give you over J, this will give you all the components of only K for the matrix A, KK. Because when J equal to K, the delta function will be equal to 1. When J is different from K, the delta function is equal to 0. So all the terms that has J not equal to K are zeros, but all the terms that J equal to K will be equal to 1, and you will end up with AKK. And what's the summation over K for AKK? What? Trace of A. So this is just the last property. So now let's go and define how to do matrix diagonalization using this similarity transformation. So again, the main purpose of this similarity transformation is to be able to transform a matrix in a set of bases to another matrix in another set of bases, which is easier to handle and help us solve the problem. So to the diagonalization of matrix. So first of all, let's define for an operator or a matrix matrix A that's defined in matrix A described or defined with or n set of bases. So this matrix is defined in set of bases EI. So this matrix is defined in or defined using set of bases EI. Let's define a new set of bases. So the operator is defined using a set of bases EI, and now let's define the same operator using a different set of bases, and those set of bases, the new set of bases is xj, where xj is equal to j from 1 to n, I from 1 to n, Sij EI. So the xj are the eigenvectors of matrix A. So if we have a matrix A and the matrix A is defined, or the operator is defined using a set of bases E sub I, now we will define a new set of bases, and this new set of bases is just the eigenvectors of the matrix A. So we knew how to get the eigenvectors of the matrix A, and we'll be doing this during this whole lecture. Now I will show you how to get again the eigenvectors. So the eigenvectors will form the new basis for the operator A or the matrix A. And Sij the matrix Sij is the transformation matrix, and it is nothing more than Sij is the transformation matrix, and it is the ith component in the unprimed, or the E sub j, and unprimed basis of the jth eigenvector. The jth eigenvector of xj. So how to form it? This would be matrix X. So you will get all the eigenvectors of the matrix A and just align them in column by column. So this will be the eigenvector number 1 of the matrix, eigenvector number 2 of the matrix, eigenvector number 3 of the matrix, and so on up to xn, the eigenvector n of the matrix. So the transformation matrix would be just the matrix composed of every column of the matrix would be what? One of the eigenvectors of the matrix A. So this is how we will form the matrix S. So if we have the linear operator A, the linear operator A in the transformed basis now will be just A primed. So we started with A in the unprimed bases, which are E sub I, and then we transformed A to the primed bases, and the transformation will be just the similarity transformation, S minus 1 A S. So you have a matrix A Using the similarity transformation, you will transform it to a matrix A prime. And again, the transformation matrix is just the eigenvectors. Every column of the transformation matrix is the eigenvectors of the matrix A. So you will use this similarity transformation to obtain the matrix A is the new primed basis. So to write this in a matrix format, this will be just summation over K multiplied by summation over L for the inverse of the transformation matrix IK multiplied by the matrix, original matrix A sub KL SL sub J. So now I can rewrite this as summation over K, summation over L of S minus 1 I K again, and AKL of, I can remove this one, and I can write it as AKL X J L. And what's this? This is just lambda sub j from the eigenvalue problem, lambda sub j xj sub k, and again this is lambda multiplied by s kj. So if you take this and substitute it here, this will give you summation under k over k, and this is lambda j s minus 1 I k s kg. So this term here is nothing more than a component of the identity matrix, and in this case the components of the identity matrix you can write it as the canonical delta function, because the identity matrix, let's say if there's 1 0 0 0 1 0 0 0 1, so A ij, so if it is equal to delta ij, so if it is I equal to j, so 1 1 will be 1, 2 2 will be 1, 3 3 will be 1. So the components of the identity matrix is exactly the same as the canonical delta function here. So when you do this and substitute for the identity matrix component or the canonical delta matrix here, you will end up with summation over k for lambda j delta ij. And what's this? This is over k. So this will give you lambda j for delta ij. So what's this? I can write this as what? I can write this as what? Lambda j, let's say lambda j is 1. So lambda 1 and ij, I equal to j, so 1 1. So this will be what? Lambda 1. And then when I does not equal to j, this will be equal to what? 0. So I transformed my matrix to what? The original matrix. I transformed the original matrix, which was the matrix A, using the similarity transformation to a diagonal matrix that will have only the eigenvalues of the original matrix. So the beauty of the diagonalization technique here is to be able to do what? To transform your original matrix, which is a sparse matrix. It has lots of elements, and you will not be able to solve the system of linear algebraic equation. You transform it to a new matrix, which is a diagonal matrix, and all the components of the diagonal matrix are the eigenvalues of the matrix A. Now you will be able to use it to solve the linear system of equations. So let's look at a couple of examples, but before we look at those couple of examples, we have to define things here. So any matrix with distinct eigenvalues, meaning that your eigenvalues are different, they are not the same, can be diagonalized. So if you have a matrix with distinct eigenvalues, you can diagonalize the matrix. If the eigenvalues are degenerate, meaning that you have n of those eigenvalues are similar, are the same. So in this case, they are degenerate, may or may not have linearly independent eigenvectors so if no, it cannot be diagonalized. So let's see a couple of examples here how to diagonalize a matrix. And we will study two cases. One case when lambdas are distinct, so it's non-degenerate case, and the other one is the case when you have a degenerate eigenvalue. So diagonalizing a matrix A with non-degenerate eigenvalues. So let's assume that our matrix is just 1, 3, minus 1, 5. I want all of you to concentrate in this process because this is show you how to diagonalize a matrix, for example, from being a matrix. This is not a sparse matrix, this is just 2 by 2, but this is just an example to show you how to diagonalize this matrix. So we knew that the eigenvalue problem is A u equal to lambda u, where u is what? Eigenvectors of the matrix A, and lambda is the eigenvalue of the matrix A. So what is the determinant of A? Is equal to 5, and this is what? Plus 3 is 8. This is 8. The characteristic equation is just determinant of A minus lambda I is equal to what? Equal to 0. And this will give you 1 minus lambda multiplied by 5 minus lambda plus 3. This will lead to lambda square minus 6 lambda plus 8 equal to 0. And from here, this is lambda minus 4 multiplied by lambda minus 2 equal to 0. In this case, lambda 1 will be equal to 4, and lambda 2 will be equal to 2. So this is usually the way how we will calculate the eigenvalues for a matrix like matrix A. So the first step is to calculate the eigenvalues. How to calculate the eigenvalues is just by calculating the characteristic equation. Solve the characteristic equation, you will obtain eigenvalues. Then how to calculate the eigenvectors? Do you remember how to calculate the eigenvectors? you will take one of the eigenvalues and then substitute in what? In the eigenvalue problem or eigenvalue equation. And in this case, you will be able to calculate the first eigenvector that's corresponding to the first eigenvalue. So let's do this. So it will be, here is the eigenvalue problem, AU equal to lambda U. So all what we will do is get A is 1, 3 minus 1, 5, and now U is just x1 and x2. So it's a vector in two-dimension vector space. It has two components, x1 and x2, equal to, what's lambda 1? So we'll call this 1, 1, 1. So this is 4 multiplied by u1 is again is x1 and x2. So this will give us two equations, x1 plus 3x2 equal to 4x1, and the second equation is negative x1 plus 5x2 is equal to 4x2. If you got those equations, you can rewrite them as 3x1 plus 3x2 equal to 0 and negative x1 plus x2 equal to 0. Those are the two equations that you want to solve. And again, you will notice that are they linearly dependent or independent, those two equations? Linearly dependent, because one is multiplication 3 multiplied by the other. So they are linearly dependent. This equation is just 3 by the second equation. Yes, guys? So if you have a linear correlation between those two lines, this means that they are linearly dependent. This is why you have number of equation, number of linearly independent equation is how many? Only one. And how many unknown? Two. So I have infinitely many solutions. It depends on the first value will pick for x1, it will give you the x2. Yes, guys? So this is why for homogeneous equation, this is a homogeneous equation. When you solve, you do not have a unique solution for x1 and x2, because here the number of equations are what? Are less than the number of unknowns. So in this case, I will pick x1 equal to a. And what's x2? From here, x1 equal to a, so x2 is equal to a. So I have infinitely many solutions. If a equal to 1, x1 will be 1, and the other one will be 1. If x2 is equal to 2, a equal to 2, it will be 2 and 2, and so on. If this is not a homogeneous, if it is, let's say, inhomogeneous equation, and I have two separate equations, I will have what? I have distinct values. So this is x1 is this, and a and x2 is a. So what's u1? A and a. So it's a multiplied by 1 and 1. So what about the other eigenvector? How can I get the other eigenvector, guys? Huh? Same process. So I will do what? I will do the equation is 1, 3, negative 1, 5 multiplied by x1, x2 equal to 2. The other eigenvector value now is 2. And from this equation, I will get x1 plus 3x2 equal to 2x1, and minus x1 plus 5x2 equal to 2x2, and this will give me minus x1 plus 3x2 equal to 0, and minus x1 plus 3x2 is equal to 0. Again, are they linearly independent or linearly dependent? Why? one is 1 multiplied by the other. So actually they are one equation, it's not two. Again, I will have what? Infinitely many solution for A and B, for A, x1 and x2. It depends on what? It depends on the value that you will put for x1 or x2. So if we pick x1 to be B in this case, what's x2? Yeah, so if we pick x1 to be B, the other one will be 1/3, or maybe this will be 3B and this will be B. So if you pick x2 is equal to B, x1 will be 3B. So in this case I can write u2 as what? B multiplied by the vector 3 and 1. So A and B are arbitrary constants. Yes, we just pick the arbitrary constant A and B. So we pick them, we can pick A and B so that U1 and U2 are normalized. What does it mean normalized? The vectors U1 and U2, normalized vector. You remember in vectors, if I have a vector A, to normalize the vector A, all what you will do is what? Just divide this vector by what? By the amplitude, and this will give you what? The normalized vector, the unit vector. So we can do this for those two vectors. How to normalize them? What's the amplitude of the first one? Square root of what? 2. And what's the amplitude of the second one? Square root of what? 10. 3 squared plus 1 squared is 10, but you have b squared in front, which is b square root of 10. So you divide here by b square root of 10, and you divide over there by a square root of 2. So this will give you what? u1 normalized will be just 1 over the square root of 2 multiplied by what? 1 and 1. And u2 normalized will be just 1 over the square root of 10, and this will be what? 3 and 1. Okay, guys? So we started with matrix A. What we did then? Find the eigenvalues first. Then we found the eigenvectors that are corresponding to the eigenvalues. And then those are the normalized vectors of the matrix A. Okay? Do the two eigenvectors compose a basis set for the two-dimensional vector space or not? So we have u1 and u2. Are they linearly independent or linearly dependent?
Independent.
What do you say? Independent. Why? I have one is A11, the other one is what? B31. Is there any relation between those two vectors? No, so they are what? Linearly independent. So they can form a basis. So in this case, this is the third property. We got the eigenvalues first and the eigenvectors, and then number 3, the completeness of this solution. Completeness of u1 and u2 to form a basis. So they will form a basis. So any vector, let's assume a vector in two-dimensional vector space that has components alpha and beta. Any vector in two-dimensional vector space that has two dimension can be written as what? Can be written or expanded in terms of u1 1 and 1, and U2 3 and 1. So I can write any vector in terms of U1 and U2. And show you this. I have a vector that has a components alpha and beta. I can write it as alpha and beta equal to some constant multiplied by the vector U1 plus another constant multiplied by the vector U2. Alpha will be what? If you put this as 1, 1, and this as what? 3 and 1. So alpha will be what? Alpha will be C1, C multiplied by 1 is 1, plus 3D. So this is 3 plus C plus 3D, and beta will be what? C plus D, and then you can get the values for C and D, and here will be 3 beta minus alpha over 2, and D equal to alpha minus beta over 2. So this is just to show you that we got the eigenvectors of the matrix A. Then we want to make sure that those eigenvectors will form a basis for the linear vector space. How to make sure that those two vectors will form a basis? Try to see if you can compose or expand any vector in the linear vector space in those two, using those two vectors, using the basis. And this is what we showed here. Then now, how to diagonalize the matrix? And this is the ultimate step that we are looking for. We want to diagonalize this matrix. Then I can use the matrix diagonalization technique. The matrix diagonalization technique, matrix, we just matrix diagonalization, they sometimes call it Jordan canonical form. So we just showed how to do it. So let's go and do it for this example. Again, the transformation matrix S is what? When we just described the first, at the very early beginning of this lecture, we stated that the transformation matrix S will be composed of what? The eigenvectors of the matrix A. And every eigenvector will be what? A column of the matrix. So the matrix will be just what? U1 and U2. Yes, guys? So the matrix is composed of the first eigenvector and the second eigenvector. So this will be what? What's the first eigenvector? And what's the second eigenvector? 3, 1. How to get the inverse of S1? So the inverse is 1 over the determinant of what? S multiplied by the cofactor, yes, of 1, 1, 2, 1, yes, guys, and then 1, 2, 2, 2. Yes, guys, this is how to get an inverse of a matrix. What's the determinant? Is equal to 1 minus 3 is what? And what's the cofactor? C11. C11 is just to cross this, and this is C11, so it will be what? 1. And C21, this is C21. Then you put this, so it will be negative 3. Equal to what? Negative 3. And C12 is what? Negative 1. And C22 is what? Equal to what? 1. So when you do this, you will get S minus 1 equal to 1/2. We took the minus sign inside, so this will give us what? Will give us minus 1, 3, 1 minus 1. Yes, guys? Yes, guys? So this is what? S minus 1. Now, to make sure that this is indeed the inverse of the transformation matrix, what should we do?
Multiply the 2 and see it.
Exactly. Multiply the 2. This will give you what?
The inverse or identity.
So 1, 3, 1, 1. Multiplied by what? Half. And this will be what? Minus 1, 3, 1 minus 1. You will notice that this is 1, 1, 0, 0. If you perform this. So now this is indeed what? The transformation matrix. We pick up a good transformation matrix. So let's now apply the similarity transformation to transform the matrix A to the matrix what? B. So the new matrix is called what? B, and it is coming from S minus 1 A S. Yes, guys? Apply now. What's S minus 1? Half minus 1, 1, 3 minus 1. And what's A? Original matrix is what? 1, 3 minus 1 and what? And 5. And the S is 1, 3, 1, 1. Just multiply those two first, and this will give you half minus 4, 12, 2 minus 2. Then multiply it by 1, 3, 1, 1. This will give you half 8, 0, 0, 4. Then this will give you 4, 0, 0, 2. What's this, guys? A diagonal matrix. But what's those? What? Lambdas. This is lambda 1 and this is lambda 2. Yes? Yes, guys? So now what I did is I diagonalize a matrix A to a matrix B and make it a diagonal matrix where the diagonal is composed of the non-degenerate, distinct eigenvalues. Okay, guys? And this is a very beautiful property of the similarity transformation. I will be able, if I have a very sparse matrix, a million by million, to do the just diagonalization using what? The similarity transformation, and I will transform the matrix to just a diagonal matrix. It will be very easy to work with this diagonal matrix, because why? It has exactly the same what? Property as the original matrix. It's similar to the original matrix. So I can use it and do, let's say, further work. It will be easier to work with this matrix. So I will stop here today, and then next time I will give the case for a degenerate case. But before I will go, just discover that there is, I think, a mistake in homework problem number 4. There is a typo mistake. So all the problem, by the way, guys, all the problems are taken from the back of the book, back of the chapter. So if you find a problem, just review the back of the chapter. So problem number 4. So this is homework number 2. Problem number 4 in the third equation. It is changed from I think it was written like x to 2, change it to 2x, 2x2. And this problem is problem what, 1018 or 218? What's the problem? 1018. It's chapter 10, number 18. So all the problems are coming from the book. So if you have any doubt, just look for the statement of the problem in the back of the chapter, and you will be able to find if it is written or there is a typo or something like this. Sorry for the mistake. Thank you so much.